Welcome to the viewers. So far, I have been delivering lectures in structural analysis, RCC, etc. Now, I have planned to give a series of lectures in strength of materials. To start with, we will start an important topic on beams, bending moment, and shear force. This is lecture number. This is lecture number 131, which will be dealing with the beams, bending moment, shear force, etc. And this is about me, you'll be knowing, right? And this lecture will be useful for second year students, not only for civil engineering. It will be useful for mechanical engineering, aeronautical engineering, etc. And also architectural students. This will be useful. It's a very basic topic, but a very important topic. When you take, whether it is a civil engineering structure or uh, anything, one must know how a particular structure or the particular component of the structure will behave, and what about the loading. So if these are known, then how to analyze, because getting the bending moment and getting the shear force are very important for the design of the structure. And any structure, maybe steel structure or RCC structure or pre-stressed concrete structure, any structure, this topic is very important. And one must know whether the structure will behave as a cantilever or a simply support or continuous beam, etc. And also, given a load, the loading may be a concentrated load, maybe UDL, maybe uniformly varying load, how to deal with the different types of loadings. We are going to discuss only the basics in this lecture. What are the different types of loadings, how to deal with them, etc. And then from next lecture onwards, we will do numerical examples. Now, we will discuss about beams, bending moment, and shear force. We will discuss the definition for beam. A beam, actually, this is a very general, simplified definition. A beam is a horizontal structural member in a building to resist the lateral loads applied to the beam axis. The mode of deflection of a beam is primarily by bending. So this is a very basic definition, because a beam need not be always horizontal. It can be inclined, it can be curved, it can be almost vertical also, right? So similarly, to resist lateral loads applied to the beam axis. A lateral load may be an inclined load, maybe a moment, anything. So it is a basic definition to understand what is a beam. A beam is a horizontal structural member in a building to resist the lateral loads applied to the beam axis. The mode of deflection, the deformation of a beam, is primarily by bending. Right? That is the basic definition for beam. We will discuss about the different types of loads, different types of supports. There are several classifications. Based on support conditions is one classification. That is what we are going to concentrate now. Based on the axis, it can be classified as straight beam, curved beam, etc. Beams curved in the vertical direction, curved in the horizontal, beams curved in plan also. Suppose we consider a beam in the case of a bridge, the beam may be straight or beam may be curved. Based on the inclination of the axis, horizontal beam or inclined beam, sometimes it will be vertical also, will be called as a beam. It can be vertical also. And based on the unknown reaction components, namely statically determinate, statically indeterminate. Of course, it is too early, but however, there are three basic conditions of equilibrium. If a structure can be completely analyzed namely determination of shear force, determination of bending moment, deflection, slope, etc., by using only the conditions of equilibrium. In the case of two-dimensional structures, we have got three equations: sigma v equals 0, sigma h equals 0, and sigma m equals 0. If a structure can be completely analyzed by only using these three conditions of equilibrium, the structure is called a statically determinate structure. If these conditions are not sufficient, these conditions alone are not sufficient, then we call the structure statically indeterminate. Right. So these are various classifications. Now we are going to concentrate only on the first classification to start with. Right. Types of support. And the bending moment is what is bending moment? What is shear force? We will discuss. We will discuss about the sign conventions, and we will discuss what is a bending moment diagram, what is a shear force diagram. So this alone will be discussed in this lecture. So based on the support conditions, the beam can be a simply supported beam. I'm not going to discuss deeper into these things. We'll discuss only what is required. So this is a hinged support. This is a roller support. It will be marked like this. It will be drawn like this. So the reactions at the two ends are vertical. Of course, it is only for vertical loading. Suppose if there is an inclined load, then there will be horizontal reaction also. Therefore, we'll just discuss only the basics now. Reaction at the two ends are vertical for vertical loading. Free to rotate at both ends. So this is free to rotate. This is also free to rotate. This again we will discuss little later, right? Theta A is possible. The rotation at A is possible. You can imagine the hinge provided for fixing the shutter in a door or shutter in a window. So at the joint, it will allow only rotation. You can open the door, you can close the door, but it cannot be moved in the vertical direction or in the lateral direction. No displacement is possible. No displacement is possible. Displacements are 0. Delta A is 0. OA is 0. Delta A or OA is 0. Here, the vertical displacement is 0. Rotation is possible. So theta B is possible. And here again, delta B or OB is equal to 0. But in the case of a roller support, if it is given like this, we will not be able to distinguish. If it is given like this, the roller is free to move in the horizontal direction. Because these basics will be helpful throughout the career. Fundamentals, but right. This is an overhanging beam, or a simply supported beam with an overhang on one side. Here again, overhanging on both sides. Overhanging, it's an overhanging beam, overhanging on both sides. So this is a cantilever, one end fixed and the other end free. It is free, that is no support. Here it is fixed. This is called as a cantilever beam or cantilever. So now these beams we have discussed so far, namely simply supported, or beam with one side overhang, or beam with both sides overhang, or a cantilever. Again, basics only, right? So these are all can be completely analyzed only with the help of the equations of equilibrium. They are called statically determinate structures. Now the types of beam we are going to discuss hereafter will be statically indeterminate beams. Namely, a proper cantilever is a statically indeterminate beam. And fixed beam is a statically indeterminate beam. That is, the basic conditions of equilibrium alone will not be sufficient for the determination of bending moment or shear force or slope or deflection. We have to look for additional conditions. That is what is called statically indeterminate. Right. Now, continuous beam, resting on more than two supports, continuous beam. So these are all statically indeterminate beams. Now here, theta A equal to 0, theta B equal to 0, delta A 0, delta B 0. The effect of fixing the beam is to make the end slope equal to 0. When the beam is loaded, the beam will be straight from both ends. It will be straight for some distance, and then only it will start deflecting. Theta A equal to 0, theta B equal to 0. Right. There is another term called kinematic indeterminacy. Again, it is too early. Kinematic indeterminacy means number of possible joint displacements. A is fully fixed. No horizontal displacement possible, no vertical displacement possible, and also no rotation is possible. Both at B also, same thing. No displacement is possible. No displacement at joint A or B is possible. Therefore, it is kinematically determinate. Kinematic indeterminacy refers to number of possible joint displacements. Both joints are fixed, no displacement is possible. Therefore, it is kinematically determinate. Right. Now, coming to types of loads. We have point load or concentrated load. So, load which is considered to act at a point. Actually, knife edge contacts are neither possible nor desirable. So, in actual practice, the load has to be distributed over some definite area. We just consider as a point load. That's all. The area of distribution may be small or large, but the load will be distributed over a small area. For example, the column in a structure transmits the load to the beam. We idealize this load as a concentrated load. The beam is idealized as a line, and the load is also assumed to be a point load. Actually, practically, knife edge loads are neither possible nor desirable. See, in the analysis of structure, the design of structure, we make so many assumptions to simplify our analysis, to seek the solution for a particular problem. We make so many assumptions. Every topic will start with some assumptions, right? So this is a beam with some concentrated loads. Now, next type of load is that of a distributed load. Loads which act over some area or over entire area or some length or over the entire length. That is what is called distributed loading. So the distributed loads are measured by their intensity. For example, coming to this point load, it is a point load. The unit will be the magnitude of the load only, namely 40 kilonewton, 50 kilonewton, 150 kilonewton, like that. That is the unit for the load, where that is for the point load. Coming to the intensity of UDL, it is the force per meter, force per unit distance. UDL will be, the intensity will be mentioned because unit is very important, right? Kilonewton per meter. If it is on a slab, the load per unit area, kilonewton per square meter. If it is on a beam, it is kilonewton per meter, or Newton per meter or Newton per millimeter, whatever it may be, force per unit distance. If it is on an area, it is force per unit area, namely kilonewton per square meter, like that. This is how we'll have to represent the unit for the forces. Now, coming to a beam, we just idealize this as a line only, as below. Now, if a beam is subjected to a load of wall of uniform height in a multi-story building, on a beam, suppose the beam consists of a wall of uniform height for some distance, a wall of varying height for some distance. So this will be represented as a uniformly distributed load. This is represented as a line. These supports are represented like this. It is UDL, so many kilonewton per meter. So measuring the height, width, and the length density of material, etc. We just calculate. So now we have to concentrate only on this. But how it comes, you must have an idea. That is right. Now this is uniformly varying load. Varying load will be given as W1 per meter and at one end to W2 per meter and at the other end. Uniformly varying load. In the analysis, dealing with this is straight and simple. But coming to this we will have to assume as a rectangle and a triangle, so that the calculations will be comfortable. Either you can consider this as a rectangle and a triangle, or two triangles. So this as the base and joining this point, and the next triangle with this as the base and connecting to this point. So you can just consider this as a area consisting of two triangles, or a rectangle and a triangle. These are all simple but very important. Right. Now, uniformly distributed load, just now we have discussed, it is represented as W per meter and uniform intensity. Uniformly varying load, UVL, uniformly varying load, W1 per meter and to W2 per meter and. Intensity varies from one end to the other end. Linearly varying load. Sometimes we call this as a triangularly distributed load. That is, at one end it is 0, at the other end it is maximum. So many kilonewton per meter. The ordinate here will be represented as so many kilonewton per meter. Right. And another type of loading is that of a couple or moment. So by providing some member like this or some bracket like this, you can apply a horizontal force at some distance. Horizontal force at some distance. If this is given, this will transmit an axial force of F along the axis of the member. Primarily, in the case of beams, we consider bending moment and a shear force only. Axial force will not just consider. That is considered to be negligible, right? So this will transmit an axial force of F and a moment of F into H2. That is, this is how it is represented. So F into H2 is the anticlockwise moment to which the beam will be subjected to at this point. Similarly, this will be equivalent to an axial force of P. I will give explanation for this also little later. And P into H1, the horizontal, the moment at this point, the clockwise moment at this point is M equal to P into H1. So if it is given like this, one need not get confused, right? Coming to the types of support, a hinged support, roller support, and a fixed support. So as I told, a hinge will not move in the horizontal direction, will not move in the vertical direction. Therefore, two reactions are possible. When I apply a force, reaction horizontal and reaction vertical are possible here. Here, only vertical reaction is possible, because later discussion, these basics will be very useful actually. So only vertical reaction is possible. It cannot take any moment. Any non-zero moment will make it rotate. Any horizontal force will allow the beam to move in the horizontal direction because of the rollers. So here it is completely fixed. So no displacement is possible. Horizontal, vertical, rotation, nothing is possible, right? So no degree of freedom here. No degree of freedom here. So that is what is stated here. Hinged support will have two reaction components and 1 degree of, it is free to rotate. Example, the door hinge or hinge in the window connecting the frame and the shutter. Roller support. We have one reaction component, only a reaction component perpendicular to the plane of rollers. Other 2 degrees of freedom. Here, 3 reactions are possible, no degree of freedom. The hinge is position fixed, only rotation is allowed, right? Here I told that there will be a vertical reaction component. it may be provided like this also. Suppose in the truss, this may be a hinge or this may be a roller. Now, horizontal reaction is possible. A reaction component perpendicular to the plane of rollers, because sometimes this roller support will be provided inclined also. Right. Now, coming to the definitions, bending moment is defined as the algebraic sum of moment of all the forces acting on any one part or one side of the section of the beam. Only later I have realized I have not provided a sketch here. That would have been more useful. Anyway, when you consider a beam loaded, suppose if you want to find out the bending moment at a particular section, consider the forces either to the left of the cut section or right of the cut section and find out the moment. We know moment equal to the force into the perpendicular distance. Moment into perpendicular distance. Now, we know that algebraic sum of all the moments about any section is equal to 0. But that is, when you consider the moment of the forces acting on the left as well as on the right, we know sigma m equal to 0. Algebraic sum of all the moments about any section is equal to 0. So, when you want to find out the bending moment, consider the forces either to the left of the cut section or to the right of the cut section. Right? So, it's defined as the algebraic sum of moment of all the forces acting on any one part or one side of the section of the beam. Here again, it is given as a beam. It's a basic definition. The structure may be a beam, maybe a slab, maybe a bridge, maybe an arch, maybe a suspension bridge, anything. But to start with, we just bending moment is defined as the algebraic sum of moment of all the forces acting on any one part or acting on any one side of the section of the beam. Similarly, shear force is defined as the algebraic sum of all the forces, acting on any one part. Suppose the beam is horizontal, then we have to consider the vertical force. All the vertical forces acting on, suppose if the force is inclined, we will be resolving in the vertical direction and horizontal direction. Shear force is defined as the algebraic sum of all the forces. General definition, if it is a horizontal beam, all the vertical forces acting on any one part or one side. Here again, if you add all the forces in a beam, considering the right support, left support, all the loads means the reactions at the left support, reaction at the right support. If everything is considered, we know sigma V equal to 0. Algebraic sum of all the forces in the vertical direction equal to 0 for satisfying the equilibrium. Therefore, for finding out the shear force at any one section, we have to consider all the forces to the left of the section or to the right of the section only. Right. Now, next is the bending moment diagram. We will be calculating the bending moment and the shear force at various points along the length of the beam, and we will be just plotting. It is a graphical representation. Bending moment diagram is a graphical representation of the variation of bending moment. What is the, suppose a beam is of 5 meters length, subject to different kinds of loading. What is the bending moment at 1 meter from the left end, 2 meters, 3 meters, like that, and how it varies, whether it is going to vary as a constant or linear variation or second degree variation or cubic variation. So that is the essence of this topic actually. That's what we are going to discuss. How to deal with various loadings, how to find out the bending moment, and how to plot the bending moment diagram, similarly shear force diagram. So bending moment diagram is a graphical representation of the variation of the bending moment along the length of the beam. Again, general definition, length of the beam or member or structure. That this need not be considered now. This definition, beam, will be sufficient for the time being. Similarly, shear force. A shear force diagram is a graphical representation of the variation of shear force along the length of the beam. So on just looking at the shear force diagram, we will be able to find out what is the value of shear force to which a particular section will have to be designed. Because once if you know the bending moment and shear force, that there are different codes for different materials. RCC means IS 456 2000. Steel means IS 800. So the respective code books will take care of the guidance for the design, how to design, what are the formulas that are to be used. All those things will be guided. But analysis, one will have to be familiar. How to find out the bending moment, what is the variation, what is the shear force for which you have to design the structure, what is the bending moment for which you have to design the structure. That only we have to find out. The ordinate of the shear force diagram at any section gives the value of shear force at that section due to the given loading or fixed load push, because later we are going to discuss about moving loads also. So that is why we have to be very specific, right? So similarly, the ordinate of the bending moment diagram at any section gives the value of bending moment at that section due to the given fixed load positions on the beam. Suppose we consider a beam of 10 meters length, at 4 meters, whatever we get in the shear force diagram will be the shear force at that section. Whatever we get, the ordinate that we get at 4 meters for the left hand support will be the bending moment for that section. For that, we have to design the structure. So that is the unfortunate thing is I didn't have diagrams like this. Anyway, we are going to discuss this topic only throughout. Right. Now coming to sign convention. Sign convention for shear force, left up, right down is positive. This is the section of a beam. Left up, right down is positive. Similarly, left down, right up is negative. Positive shear force, negative shear force. These things will elaborately discuss in the problems. Similarly, this is left up, right down is positive. That is, a clockwise shear will be positive. A clockwise shear, that is, this is left up, right down. So this is clockwise. A clockwise shear is positive and anti-clockwise shear is negative. Coming to bending moment. Left of the section, left clockwise is positive. Left clockwise is positive. Right anti-clockwise is positive. Right. So this is positive bending moment. Sagging bending moment. It's otherwise called a sagging bending moment. This will cause the beam to sag like this with concavity upward. This is what is called a sagging bending moment. So if a beam bends like this, top will be under compression, bottom will be under tension. Suppose if it is a concrete beam will be strong in compression, weak under tension. We have to provide the steel reinforcement only where tension occurs. Negative bending moment. Negative bending moment is like this. Hugging bending moment. That is, left anti-clockwise is positive, negative. Right clockwise is negative. So these things will be clear when we discuss about problem, but knowledge of this is very, very essential. Negative bending moment is hugging bending moment. The convexity will be upwards. Tension will occur on the top. Suppose we take a cantilever. When it is loaded like this, it will bend like this. So the behavior will be like this. So here tension occurs at the top. Suppose if it is a cantilever beam or sunshade, we have to provide the steel at the top, where tension occurs. So here again, it is a cantilever on the right hand side, cantilevering on the right hand side. Here again, it is at the top. Tension occurs at the top. Now, again, this will be explained. Anyway, now hugging, that is hugging bending. So these two, whether it is on the left hand side or on the right hand side, hugging bending moment with the tension at the top. Right. Now, how to deal with the different loads? Suppose if a structure is subjected to uniformly distributed load, right? Now, the total load will be considered to act at the center of gravity of this. This is the given load, 40 kN per meter, acting over a length of 3 meters. So 40 kN per meter into 3 meters equal to 120 kilonewton. So total load equal to 40 into 3, 120. So 120 kilonewton is assumed to act at the center of the load, center of the UDL, because it is uniformly distributed load. So when we want to find out the bending moment about the support B, about actually support is not marked, assuming B as a support. If you want to find out, even if it is not a support, if you want to find out the bending moment about the point B due to this loading, it is 120 kilonewton, 40 into 3, 120 into the distance up to the point B, that is 2 meters plus 1.5, so 3.5. So the bending moment due to this loading about this point B will be 120 into 3.5, 2 plus 1.5, 3.5, force into perpendicular distance. So this concept we will be using throughout. Similarly, if it is uniformly varying load, total load equal to half into base into height, half into 4 meters into 50 equal to 100 kilonewton. The 100 kilonewton load is assumed to act at the center of gravity of that area. That is, center of gravity for this triangular load, it will be 1/3 from the base, namely 1/3 of 4 meters from B, 1/3 of 4 meters from here, or 2/3 of 4 meters from this apex, 2/3. This is what is very important, simple but very important. This is where people used to struggle, right? How to find out the bending moment due to uniformly varying load, etc. Right. So about this, the moment equal to 100 into 1/3 of 4. If you want to find out the bending moment due to this load about the point A, it is 100. The load is 100. Half into 4 into 50, 100 into the distance up to the point A. Distance is 2/3 of 4 plus 2 meters. Here we normally commit a mistake, that is when you want to take a moment about the point A, better have some pencil or your finger at that point, so that you have to refer all the distances up to that point. So, right. Total load and acting at 2 plus 8 by 3. 2 plus 8 by 3, that is from here 2 plus 8 by 3 from A, or 1/3 of 4 from B. Right. Next is another case is that of a moment. So, already we have discussed a beam with a vertical member plus a horizontal load. Now coming to this, here a bent is provided like this, and here you apply some load, because you have got so many complicated structures, how the load will get transmitted and how we have to deal with that loading. The basics is very important, right? Suppose there is a load here. Now this is equivalent to a vertical load 20 kilonewton here plus an anti-clockwise moment 20 into 1. So an anti-clockwise moment 20 into 1 kilonewton meter. So how this load is transmitted as axial load here, we will just give a better example in the subsequent examples. So now time being, you just take it as say a vertical load at the free end plus that of an anti-clockwise moment of Only when we know this, we will be able to find out the bending moment here properly. So this loading is to be properly converted as the loadings at the free end. Then analysis will be simple. So that is something about. Similarly, as I told, there is a trapezium load means we have to consider as two triangles or one rectangle and a triangle. Right. I think that will be the basics. With these basics, we'll do number of examples in the subsequent lectures. So with these basics, let us close down this lecture. So I thank the viewers for the patient hearing. Thank you. Thank you.